Welcome back to an introduction to Earth Science. I'm your professor, Dave Cocchiarella. This is Chapter 7 from Foundations of Earth Science, the 8th edition, our textbook, brought to you by Pearson Education, and of course written by Lutgens and Tarbuck. In Chapter 6 of this course, we started our conversation about the effects of plate tectonics, the grand unifying theory of geology. We started that conversation with earthquakes and mountain building, and now in Chapter 7, we are going to move on to volcanoes and other types of igneous activity. We will start our conversation about volcanoes and other types of igneous activity with a quick look at two of the most famous volcanoes, for the United States at least, Mount St. Helens and Kilauea. So St. Helens exploded, more of an explosion than an eruption, back in 1980. And when it did so, it blew off out of the north rim. So you're looking at the north facing side of Mount St. Helens. This is the way it looked before 1980, and this is the way it looked after its 1980 explosion. 1,350 feet of the mountain were blown off. The largest eruption in North America, again, lowered that peak by 1,350 feet, destroyed all the trees in a 400 square kilometer area, and it sent mud flows 29 kilometers down the river and ejected just literally tons and tons of ash more than 18 kilometers up into the stratosphere, which is the layer above the atmospheric layer that contains all weather. So it really got that ash way up there. And of course, we'll talk later about how volcanic ash and gases can be attributed to sometimes climate cooling. All right, this is a couple of views of the trees that got blown away, quite literally, all around Mount St. Helens after that explosion. Kilauea, on the other hand, is a very non-explosive volcanic eruption. It's a different type of volcano. It's a type of volcano that produces a basaltic, low silica magma that turns into lava when it comes up on the surface of the earth. And you may have fountains from some escaping gases, but there's very little gas in the magma, so they're really quite minimal. You can be in very close proximity to any eruption. As a matter of fact, eruptions of this nature you can walk right up to on most occasions. And you can go to Hawaii today, the big island of Hawaii, go to the South Shore, and if there's a current lava flow, you can do exactly that, be very, very close to any of those lava flows. So magma, of course, is the source material for volcanic eruptions. Magma is molten rock. Now it's completely liquid, completely molten, but it does contain crystals and also some dissolved gases. When magma gets to the surface of the continent or the surface of the seafloor and it's erupted out onto the surface, then it is considered lava. And it's not just a situational difference, like it was below the surface, now it's above. Once magma reaches the surface, the depressurization of the magma does allow most of those gases to be released. So lava has actually got a slightly, or sometimes a significantly different composition than its parent magma. I talked about Kilauea being a basaltic magma or a basaltic lava flow. Basaltic magma is going to be a low silica, low gas, low viscosity magma generated by the partial melting of the upper mantle. And you mainly find basaltic magmas at oceanic crust, at the diverging centers in oceanic plate boundaries, where you have two oceanic lithospheric plates moving apart. The magma that wells up is typically, well, it is basaltic magma. It erupts highly fluid, and that term low viscosity essentially means it's highly fluid. You do find basaltic magmas at the continental crust. It collects up at the crust mantle boundary, so just below the crust, just above the mantle, right at the boundary. And that basaltic magma typically will cause the overlying continental crust to melt, and that's going to be a much more silica-rich magma, so it's going to have a higher viscosity. So when basaltic magma gets up into the continental crust and it melts that continental crust, it increases its silica content and its viscosity, and that's why a volcano like Mount St. Helens is going to explode high viscosity magma as opposed to a Kilauea that's just going to have that fluid flow. So viscosity is in fact resistance to flow. You can talk about air being the most viscous material, and then pure water, and then maybe syrup is more viscous, and then we can look at something like molasses being even more viscous than that. tar is even more viscous than that, then you'll start talking about mantle rock and solid rock. Viscosity is a substance's resistance to flow. So how can you decrease the magma's viscosity? Well, just like most other substances, if you increase the temperature, think about taking tar. It could be a lump, but if you heat that tar up, it will begin to flow. Same thing with peanut butter, even syrup. Syrup flows slowly when it's cold, much more quickly when it's warm. So you can decrease viscosity by increasing temperature, and you can also decrease the magma viscosity by decreasing the silica content. So that basaltic magma is low in silica, very fluid, where rhyolitic magma is very high in silica and it's very thick, and then andesitic magma is somewhere in between. Gas content also dictates the nature of an eruption. More gases are going to be in more violent eruptions. It's the expelling of the gases out of the magma as pressure decreases that causes the violent eruption. And there's a great analogy used throughout this chapter of the soda can. If you take a soda can and it has gas has been dissolved, carbon dioxide gas has been dissolved in the soda, when you release the pressure by popping the top, it will bubble up. And of course, if you shake it up, it's going to be a more violent release of carbon dioxide from the soda. So gas content also dictates the nature of eruptions, directly related to the composition of the magma. And the most common gas that is in magma is water vapor. As a matter of fact, much of the water on Earth was expelled or outgassed during the Earth's early bombardment period through volcanic eruptions all over the Earth. It just expelled tons and tons of gas and carbon dioxide and some other gases as well. But the water vapor was the main one. All right, so here are the properties of magma bodies. And this is a great chart to look at. Really, in the end, most magma on Earth is basaltic. There's a much smaller percentage that's andesitic and a very small percentage of rhyolitic. Because rhyolitic magma has so much silica in it, so much gas in it, and has the greatest viscosity because of the greatest amount of silica, it usually doesn't even get to the surface. It may bubble up underneath the continental crust or in the continental crust and create some uplifting and upwelling, but typically rhyolitic magma doesn't even get to the surface. The two main magmas that get to the surface are going to be your basaltic magma with the least amount of silica and your andesitic magma, which is intermediate between basaltic and rhyolitic. Of course, your basaltic magma has low silica, low gas. It also erupts at the highest temperature. That's how that basaltic magma that arrives at the mantle crust boundary can melt the overlying granitic crust. It has a very high temperature. That overlying granitic crust has a much lower melting point. Basaltic magmas have the lowest viscosity. They have the least potential or propensity to form pyroclastics, and they typically make shield volcanoes or basalt plateaus, and sometimes they're associated with what are known as cinder cones. We're going to talk about all three of those volcanic landforms. Andesitic magma is going to be of intermediate composition, meaning somewhere between basaltic and rhyolitic. It has intermediate amounts of silica, intermediate amounts of gas, intermediate amounts of, intermediate level of eruptive temperature or where it melts, intermediate viscosity, intermediate tendency to form pyroclasts, and it typically creates your composite volcanoes or your composite cones, your typical triangular shaped volcano. And so on land, what we typically see is an andesitic volcano. Remember the mountain chain, the Andes, named after that type of magma. And then the rhyolitic, again, has the most of all these things and is very, very short-lived, doesn't travel very far, very, very thick types of magma. To summarize, low silica, low viscosity, low gas content, basaltic magmas produce fluid, less violent eruptions. Okay, high silica, high viscosity, high gas content, and acidic or rhyolitic magmas, they will produce more violent eruptions. So how do we get our shield volcano? How do we get our basaltic eruption going? Typically, you have additional magma arriving at a magma chamber that is very close to the surface. In the case of Kilauea, it is over a hot spot that is below the Pacific plate. That hot spot produces additional magma that moves up through the oceanic crust, and when it arrives at that near-surface magma chamber, you begin to get an inflation of the summit. It begins to bubble up a little bit. Some fracturing going on with the rocks, some gases that are expelled, some mild, let's say, earthquakes, and then ultimately a fluid basaltic lava. So the eruption of Kilauea has been going on since 1983, and even though you see the spray here, this is just from the release of those minimal amounts of gases. This is nothing, this is a millionth of the explosive ferocity of an andesitic volcano. So explosive eruptions are triggered as pressure decreases as magma rises. So the magma is moving up through the crust. And as it moves up to the crust, less overlying rock means less pressure. And in that soda can analogy, less pressure allows the dissolved gases to form expanding bubbles. That viscous magma, viscous because again it has all that silica in it, expels with that those gases bubbling out, expels fragmented lava and gas and creates these very buoyant plumes of material. They're buoyant, these eruption columns, because the gas that's being expelled is very hot, so it's very, very low density gas, has a tremendous amount of buoyancy, and it rises up, and you get a rapid ejection of the magma. It reduces the pressure in the magma chamber, and with the reduced pressure in the magma chamber, more magma from below rushes up as well. So your high viscosity magmas, because you've got all that silica in there, that silica holds on to those gases, and the gases are trying to be expelled from the magma. The very sinuous silica tetrahedral chains holds on to the gas as long as it can, so when the gas finally is expelled from the magma, it is much more violent. 90% of all lava is basaltic. Most is erupted on the seafloor. It flows in these thin, broad sheets or ribbons. It can move 10 to 300 meters an hour, and it can move a whole lot quicker than that if it's moving downhill. Only 9% of lava on Earth is andesitic in that intermediate composition. That's what makes up our stratovolcanoes, or our our composite volcanoes. And then less than 1% is going to be rhyolitic. Thick flows, they move extraordinarily slowly, and they do not flow very far from their vents. Your basaltic flows typically are these very, very ribbonous flows, but as they cool down, they will become this more choppy and broken up and sharper flow. So when they're very, very hot, they flow very easily in these ribbons and these pools. And this is your pahoehoe magma, or I should say lava. And then your lava is the coarser, denser, sharper. And essentially it starts out this way and then slowly cools and turns into this. But you can see the red hot. And so this is very likely cooled lava, and this is a new lava flow. And so this is how non-explosive this eruption is. If you had a stick, you could walk across this lava flow. It'd probably crack and break underneath your feet, and stick that stick into that little red area, and it would catch fire. That's how close you could be to that lava flow. Now, a lot of folks would say that's not very smart, but nonetheless, that's the case. Now, when this basaltic lava flows in this very low viscosity manner, this very ropey manner, you can see the outside is crusting over. And as the outside crusts over, what's inside continues to flow, and you get these lava tubes that form. Now, this is a massive lava tube. And the Valentine Cave, it's a lava tube. But most lava tubes aren't anywhere near this big. But these big, huge lava tubes form, and the lava continues to flow. And what happens with this is once the tube forms, the lava is not exposed to the air, so it will cool much more slowly, which means in these basaltic lava flows, these flows through the lava tubes can go much further away from the central vent. And you do get lava tubes in which you still have hot magma underneath, and the roof of the lava tube collapses, and that gives you these skylights. This guy's walking across. Underwater, you get basaltic magma that flows up and turns into lava on the seafloor, and it creates these tube-like structures that get stacked up on top of each other, and very appropriately, this resembles pillows or blobs of toothpaste, and this is referred to as pillow lavas. Most of us are aware that lava is something that is extruded during a volcanic eruption, but there are other items like gases and pyroclastic materials. Gases and magma is considered to be a volatile. It's something that gets that magma charged up. That gas is under pressure, dissolved in the magma, but once the pressure is released, as that magma rises to the surface, the gas can escape from the magma, and oftentimes it does so explosively. The most abundant gases in decreasing order, and this is important because you have to understand that a lot of the water and the water vapor in the atmosphere, a lot of the water on Earth, it actually came from the rocks of the Earth during that early volcanism when much of the Earth was molten, and volcanic eruptions at the surface released tremendous amounts of water vapor. The next most abundant gas is carbon dioxide, and when we talk about the atmosphere and the composition of the atmosphere, we'll find out that the early atmosphere of the Earth actually had a tremendous amount of carbon dioxide in it. Where did it go? Well, look around you and all those green plants that didn't exist when the Earth formed, they helped to suck up that carbon dioxide. Also, sulfur dioxide and amounts of hydrogen sulfide, carbon monoxide, and helium. And of course, all these gases contribute to the atmosphere, and significant volcanic eruptions can alter global climates. And you may see that carbon dioxide and think, well, does it make the climate warmer? In most cases, the sulfur dioxide kind of makes little droplets in the upper atmosphere as well as ash up there, and tends to actually cool the atmosphere off. So something that we've seen with massive volcanic explosions is the atmosphere cools globally afterwards. All right, pyroclastic materials. I mentioned that as one of the types of materials that come out of volcanoes during eruptions, and it really is classified based on its size, from ash to cinders to bombs to blocks. And so pyroclastic materials, sometimes called tephra, is the solid stuff that comes out of volcanoes. And it comes out of a volcano, and oftentimes if it's molten magma, it freezes immediately. Sometimes it's actually rocks that are peeled off the vents of the volcano in an explosive eruption, like the volcanic blocks you see at the bottom. But if we're talking about that ash, or really a lot of this other material, we're talking about something that came out as magma and cooled very quickly. So the crystals generally didn't have time to form, and so you're really looking at volcanic glass. But that handful or two handfuls of ash in that top picture doesn't look like glass at all. But what we learn is that volcanic ash and dust is just really truly tiny pieces of volcanic glass. You also have hot ash that fuses when it's in the air. When it falls to the ground, it creates what's known as welded tuft, and basically it looks like cooled magma. Then you also have these cinders that can blow out of a volcano, and because there's still gas bubbles in the molten magma when it blows out of the volcano, as that material very rapidly cools, those gas bubbles are frozen in state, and you get these small, maybe marble size, pea size to the size of a walnut, chunks of rock that are very vascular. They have lots and lots of holes in them. And we have some of these larger blocks, these volcanic bombs, and they're called bombs because of their shape, but they come out of the volcano, generally molten, generally liquid, and the outside cools, and sometimes they'll land quite a distance away from the volcano with the outside being solid, the inside still being molten, and kind of explode, maybe in the way that napalm does. So again, volcanic bombs. And then bombs are streamlined blocks that are ejected while they're still molten. And then again, sometimes eruptions will peel chunks of rock off the side of a volcano, the inside of a volcano, and spew it out of the volcano itself. So two types of those vascular materials, scoria and pumice. Really the difference between the two is the type of magma. The top one is darker, and so you may remember the basaltic magmas, they tend to be darker, and the bottom one is lighter, and those tend to be coming from andesitic or rhyolitic magmas with a great deal more silica in them. So the scoria is a vascular rock, commonly having basaltic composition, not all that large, and largely that's what gathers around cinder cones. And then the pumice is also a vascular rock, but really very, very low density, so much so that there's enough air cavities in pumice, this very high silica rhyolitic rock, that it can actually float in water sometimes. So what is the anatomy of a volcano? This is pretty typically what you think of when you go back to your childhood drawings of a volcano. A big cinder cone, or a big cone, I should say, with a vent in the middle. But of course, we learned that there are vents that go out on lots of sides of the volcano. Volcano or volcanic landforms are typically the result of generations of volcanic activity. So what you're seeing here is layer upon layer upon layer that may have happened over many thousands or perhaps even millions of years, where one layer after the other, after the other, after the other is heaped on top of previous layers. And really it is the ability of this lava to flow, its viscosity, that determines whether you have a low mound of a shield volcano or a tall peak of our composite volcano. So Eruptions start at fissures, so the fissure is something within the surface or underneath the surface of the Earth, and as magma works its way up to the fissure and melts the localized rock, it creates a circular conduit. That's your conduit, and the conduit essentially terminates at the vent. And again, successive volcanic eruptions form your volcanic cone. The crater is the funnel-shaped depression that's at the summit. Sometimes it's formed by erosion, or sometimes it's formed by the collapse of the summit itself. Calderas are different parts of a volcano. Not all volcanoes have them, but volcanoes are much, much larger. So a crater is something that's going to be on top of a volcano like this at the end of a vent, at the end of a conduit where the vent and the top of the peak is where the crater is. A caldera is going to be a much larger, greater than 1 kilometer across, kind of hole in the ground that forms a couple different ways, but full of magma as well. So flank eruptions along the volcano, so volcanic eruptions that happen in any of these side vents, they'll create, you can barely see right there, there's a little cone right there, they'll create what's known as parasite cones, and then we also have some vents that don't emit lava at all, just emit just gases, and those are typically called fumaroles. Two types of volcanoes, well, there's three general types of volcanoes that we're going to talk about. What you typically think of is a volcano looking like this, composite, and then what we see a lot of in volcanic islands, which are shield volcanoes. And you can look at, this is a volcano, and you can see it kind of looks like a shield lying on its side. Broad dome structures build up by accumulation. So this is not one volcanic eruption, it's accumulations of many, many tens or hundreds or even thousands and thousands of lava flows with basaltic, low silica, low viscosity, very fluid magma that can flow great distances from the vent and spreads out to make these low, broad mountains. Most start out as seamounts on the bottom of the ocean and just get bigger and bigger and bigger until they break through the surface of the ocean. They become islands like the Hawaiian Islands and the Galapagos and Easter Island and the Canary Islands as well. So the big island of Hawaii is made up of, and most of our islands are made up of several volcanoes. It's a total of 5 volcanoes, including the most famous, Mauna Kea, Mauna Loa, and Kilauea. And Kilauea is the volcano that's currently erupting. And because Hawaii's islands and all these volcanoes are a function of a hot spot, meaning a spot underneath the actual oceanic crust in which magma has bubbled up to the crust mantle boundary and then broken through, and of course the Pacific plate is moving along on top of that hot spot. This is the older of the volcanoes are here. They're formed 1st, 2nd, 3rd, 4th, 5th for the big island, and there's actually a seamount out here just offshore on the southeast coast that is going to be the next island. Probably take about 10,000 years for it to get to the surface. 9 kilometers high. I think that Mauna Loa is upwards of just at 15,000 feet above sea level, and so when you consider how it goes to the bottom of the sea floor, it literally is the largest volcano on Earth. A lot of them have these large calderas, which are big holes more than a kilometer wide, in which the top of the volcano is collapsed. And you can see you have a magma chamber. Lava is fed through the mantle into the crust. And then once this magma chamber fills up, then it begins to extrude or erupt out of the different vents that you might find on the volcano itself. And that's what that looks like. And so you can see very fluid, that lava, the way it moves. Kilauea is the most studied volcano on Earth, 50 eruptions since 1823. The most recent started in 1983 and is continuing to this day. Basically, that magma chamber gets bigger and bigger and bigger as it fills with magma. Maybe you get some earthquakes going on, you get some venting of some gases, and then eventually the eruption occurs, and that's kind of what it looks like. Oops. All right. So that is your shield volcano, one of the 3 primary types of volcanoes. A second, a much smaller version, some that are much younger, they don't last very long, are these cinder cones. And these cinder cones typically form along the flanks of another volcano, and they are completely unconsolidated pyroclastic material. So tuft, some of those vascular rocks that I showed you, they blow out of a central vent. They don't go very far. They tumble down. They're very sharp and they have a lot of texture to them, so they tend to stick together nicely. They give you a nice steep angle of repose, and you get these 1, 2, 3, 400 meter high craters that are in fact cinder cones. And you don't really get an eruption once the initial eruption occurs of any more lava. It's most of this pyroclastic material. This lava that flowed out literally flowed out from the base of the volcano on the other side of this. So this is a pretty classic cinder cone. They typically are very symmetrical in nature, and they typically occur in one eruptive event that builds it, and then maybe you get some lava flow afterwards. So the last and the type of volcano that I think you typically think of when you think of volcanoes is the composite, or also known as a stratovolcano. These are the types of volcanoes you're going to find on land around the Ring of Fire, typically symmetrical, oftentimes large. They are also built in layers of cinder and ash and lava flow, but the lava is much more viscous, right? It doesn't flow very well at all. It doesn't flow like basaltic lava. It's more andesitic or rhyolitic, and so it tends to stick to the side of the volcano itself, and that results in these big, steep volcanoes, all right? Typically silica-rich, andesitic. The rhyolitic magma typically doesn't actually make its way all the way to the surface of the earth. It typically gets stuck somewhere underground. And the last truly distinguishing feature of the composite volcano, or the stratovolcano, is the fact that eruptions tend to be very violent. This is a very sticky magma, right? It's silica-rich. Those silica tetrahedrons make these long, sinuous chains, sometimes three-dimensional chains, and they tend to hold the gas in the magma longer. So the gas is trying to get out as it's less and less pressure on top of it, but the silica is holding it in. Finally, it explodes out when it gets to the top. And so these sticky magmas, these high viscosity magmas, the andesitic rhyolitic magmas, tend to also create very explosive volcanic eruptions. Types of volcanic hazards, right? 70 volcanic eruptions are expected each year, typically one large volume eruption each decade. 500 million people live near active volcanoes, and those hazards include your pyroclastic flows, your lahars, your lava flows, ash, and volcanic gases. And this is a pyroclastic flow, so this is not gas that's rising up out of a volcano. This is very hot, high-density gas that took a lot of ash and dust up, and then it cooled enough that it began to sink and it became high density. And it's literally moving toward that Jeep as a sometimes several hundred degree, many hundreds of degrees, cloud of dust and ash and gas and chunks of volcanic rock. Really dangerous and violently ugly stuff. And this is what a pyroclastic flow looks like. So your initial blow of the volcano, extraordinarily hot gases, they rise, and as they get up, they begin to cool, and they sink back down as a high-density cloud, and they just move down that volcano at 100 kilometers per hour, hot gas with incandescent ash and lava fragments. It's just really nasty stuff. So you have this low-density cloud here up on the top, and then underneath it, that denser cloud of the ash and the incandescent lava fragments and the glass and the pyroclastic materials, just really nasty stuff. And typically it's caused when that column of that hot gas just kind of collapses. And this is a classic find of evidently a human that was caught in a pyroclastic flow. This is a famous 1902 eruption in St. Pierre, where this is the town before the eruption, and this is the town after the eruption, and this entire decimation of this town occurred by a pyroclastic flow. Another occurrence with volcanic eruptions is something called a lahar, and a lahar is basically a muddy, hot flow that accompanies volcanic eruptions because of all that ash and soot and dust and those fine volcanic materials mixes with water and flows downstream, typically in channels, and you get lahars. Now, it can happen two ways. You can have just billions of tons of volcanic ash that's settled on the sides of a volcano, on the sides of a mountain, and then have a heavy rain that washes it down, creating a lahar. Or you can have a more insidious situation where, let's say, you have a glacier-topped volcano, and we have some of those in the Pacific Northwest, or just a volcano that is topped with snow all the time. If that volcano blows, all that snow and all that ice will melt and mix with that hot ash and flow downhill in what's known as a lahar. And this particular lahar, moving through what's called the Muddy River after Mount St. Helens, got to this height on the trees, and you can say, here's a human being standing. So it was a tremendous mud flow that washed down the valley, and typically they do follow those stream channels. Volcanic eruptions are capable of producing tsunamis, typically not the biggest of tsunamis. They actually, of course, produced ash. Sulfur dioxide, which of course affects air quality, creates acid rain, and sulfur dioxide creates aerosols that reflect solar energy, and then other soot and ash in the atmosphere will reflect solar energy, and that will result in atmospheric cooling. We talked very briefly about a caldera. Kind of tough to imagine exactly what we're talking about, but essentially you get a volcano that collapses for one reason or another. In this case, you have a magma chamber and a volcanic cone above it. That volcano actually collapses into the magma chamber, and you get this big, deep caldera. And then sometimes they fill up with water. Crater Lake is one of those. This little Wizard Island is actually the caldera formed, and then later that little volcanic cinder cone popped up, and that's what Wizard Island is. And so you can see this at Volcano Lake. Nonetheless, these calderas can be very, very large. And they can still contain hot magma. All right, fissure eruptions can be pretty unique and fairly devastating if they were to happen in modern day times, and very, very widespread. Essentially, you get these fissures along a long area where magma is coming up to the surface, and very liquid basaltic magma flows out of those fissures, those fractures, and they can flow for great distances because it's low viscosity, basaltic, very liquid magma. And you get one flow, and then a second flow, and then a third flow. And these layers of basalt can build up actually quite significantly. And you can see this, you can see at least two very distinct layers in this situation. And they completely cover the terrain. So sometimes they're called flood basalts. Sometimes they're called basalt plateaus because they're so liquid that, of course, it ends up sort of lying down and solidifying flat. So they typically are flat top. But there are a number of extraordinarily large flood basalts or basalt plateaus around the world. The Columbia River Gorge is an excellent example of one. Each of these are layers of basalt magma that flowed from the same eruption site over many thousands of years and created this 1,000-foot deep canyon when the Colorado River eroded its way down to try and find its base level. So this is one entire basalt floodplain or plateau, the Columbia River Gorge, that basalt. But there are actually larger ones that have been found underwater and found in other parts of the world. And so large, when we date them, they actually line up with earlier periods of atmospheric cooling, which again goes back to sort of confirming this idea that volcanic materials can affect the climate. This is an interesting feature, the volcanic neck. You have your original volcano, your conduit fills with magma that cools, and this volcanic material on the side is highly susceptible to erosion, but the igneous rock, the solid igneous rock isn't, and you end up with a volcanic neck, or sometimes they're referred to as plugs. Other intrusive types of igneous activity, magma that crystallizes in the Earth's crust that can actually displace or lift up sometimes host, or what's called country rock, forms what are known as intrusions or plutons. So we've shown you a lot of pictures over the last couple of chapters in which magma is rising up through the Earth's crust, and some of it gets to the surface in the form of a volcano, but some of it gets in place. It's that intrusive plutonic igneous rock that cools under the surface of the Earth, and it can cool fairly close to the surface of the Earth, but it cools under the surface of the Earth, and it literally displaces or moves the rock that it's being emplaced into, which is known as the country rock. And we have these intrusions, and sometimes they're called plutons. And if they're exposed by uplift and erosion, they can look like something like this. So this is the sedimentary rock below, and this is an intrusion of volcanic igneous rock, plutonic. Check that, not volcanic, plutonic igneous rock. It would cool underground. So this isn't like a flood basalt or a basalt plateau that happened on the surface. This is something that happened underground, and then everything else was eroded away. So they have this tabular, like a table shape that can be massive, and you have intrusions that are either discordant or concordant. Either they flow with the strata or they move against the strata. So here are your typical plutons, and these all individual plutons made up from individual magma chambers, and when they solidify together, the individual plutons together are typically known as a batholith. So that's a massive thing. So there's the Sierra Nevada batholith. So you have to imagine all this granite that makes up the Sierra Nevada, including this famous Half Dome and places like that, in Yosemite. All of that at one time was underground in the form of these intrusive plutonic igneous rocks that never quite made it to the surface and cooled underground. And then everything above them and around them was just simply eroded away and washed away, leaving these batholiths. And by definition, a batholith is when it's exposed. When it's underground, it's pluton. When it's exposed, it's a batholith. But there are other types. You get dikes and sills. And your sills, think of a windowsill, run flat between sedimentary strata. So they may come up here and then dislodge and actually lift up the sedimentary strata and leave a flat place right here, which is what you're looking at here. That's a sill. That's another sill. There's the sill. It's in between that sedimentary strata, right? And then you have dikes that go up, and they are discordant. The sills are concordant, and the dikes are discordant. And so you have volcanic necks, you have sills, and a laccolith is just sort of a pluton that's not quite big enough to be a batholith, but has been exposed. All right, here is a dike that's been exposed. So here's the central volcano, the central crater, and some dike moved out away from it, radiated out away from it, and this is all underground, right? And then it was eroded away by erosional forces, by weathering, and what it left is the igneous rock in the middle of the dike. And so the dikes are discordant, the sills are concordant, and they can be, as you can see, really quite large. Now, when you get cooling of igneous rock underground, oftentimes the igneous, as it cools, of course, as you know, when you heat things up, they expand. When you cool them off, they tend to contract. And so these igneous rocks will contract oftentimes in these six-sided columns and make this columnar jointing. And you can find these in a number of places out west. And they look like these columns of rock have been stacked up together. But essentially, this is one complete magma chamber that, as it cooled underground slowly, cracked into these six-sided columns, and that's what it left behind. Now, this typically happens near the surface, so the cooling is rapid enough that slow enough that crystallization occurs, but rapid enough that they're very, very small crystals or very, very fine crystals. So large intrusive bodies, again, those batholiths that essentially are exposed. Stocks are maybe an individual magma chamber that forms an individual mountain. And then your laccoliths are when you've literally lifted sedimentary rock. So down here, these layers, this strata of sedimentary rock was lying flat. All these were lying flat on top of this green one at one time until this magma chamber with this sill came out, and then it formed here and it gathered up here and it literally lifted the sedimentary rock up. And so that is going to be your laccolith. All right, so what are the origins of magma? I've talked about three different types of magma, basaltic, andesitic, and rhyolitic. And I told you that basaltic makes up about 90% of all magma, rhyolitic less than 9%, and really less than 1% is, or right around 1%, is going to be your rhyolitic, which rarely ever gets to the Earth's surface because it's so thick and sticky. But why do you have essentially two different types of magma, low silica and high silica? What happens to cause those two different types of magmas? Well, the answer is the partial melting of rocks. The partial melting of rocks that typically make up the mantle for your low silica basaltic, and then rocks that make up the existing continental crust, which typically is granitic, a high silica type of rock. Partial melting of those rocks will result in silica-rich magmas. And remember, silica has a fairly low melting point, so if you get some hot magma pushing up into granitic rock, the silica is going to melt out first, and so that magma is going to become more silica-rich. So Earth's crust and mantle are composed primarily of solid rock, and rock is composed of a variety of minerals with different melting points. Rock melts over a range of temperatures, and so incomplete melting of rock, because it's made up of different minerals that all have different melting points, rocks will melt at different times and different speeds. And so you can get complete melting of rock. That's igneous, and that's going to be magma. But magma sometimes hasn't melted everything, and you're going to have little pieces of crystals in there. So this is the mantle rock, and as you go down, so this is depth in kilometers, so 500 kilometers, really almost to the bottom of the asthenosphere, there is a geothermal gradient, meaning it gets hotter and hotter and hotter the deeper you go. And it's a pretty steep gradient for a while. Then it kind of levels out once you get past about 100 100 kilometers. Of course, that's basically just below the lithospheric plates, and it doesn't get a whole lot hotter any quicker. But what you can see is that it is always just below the melting point of crustal and of your mantle rocks. And so you don't get complete melting of those rocks. So orange is a mantle rock that's partially melted, and the yellow is going to be mantle rock that is completely melted. And you need to have these temperatures, 1,000 to 1,500 degrees, 1,500 to 2,500 degrees, to either partially melt or completely melt the rock. So the geothermal heating, the geothermal gradient, getting hotter as you go deeper, isn't enough to melt or to partially melt those rocks. So how does it happen? Well, the mantle is solid under normal conditions. As pressure increases, it increases the melting temperature. So the higher the pressure, the deeper you are, the higher the pressure, the higher the temperature it has to be to melt the rock. So the converse is also true. The less pressure, the lower the melting point. So if rock is moving in the magma, in those convection cells we talked about, yes, it's solid rock, but it's just plastic enough that there can be some movement. If rock is moving in those convection cells, when it starts to come up, every foot, every meter, every kilometer, every tens or hundreds of kilometers that it gets closer to the surface, the pressure on it decreases and decreases significantly. And as the pressure decreases, the melting point decreases, and rocks begin to partially melt and perhaps eventually even completely melt. So that partial melting of rock as pressure goes down is called decompression melting, and is triggered when confining pressure decreases. And largely, you get decompression melting of low silica, resulting in a basaltic magma, low silica rock with a partial melting of the upper mantle at spreading ridges. And so most of our spreading ridges are oceanic, so primarily occurs at oceanic ridges. The one continental spreading ridge, the East African Rift Zone, you do get basaltic magmas. But essentially, it's the decompression of that magma plume that causes the partial melting to occur, and that's what arrives at the sea floor, which then solidifies into either basalt rock or beneath the surface gabbro rock that makes up our brand new oceanic plate that eventually moves away because of the forces of plate tectonics. The other way that you can get partial melting of rock is to create a chemical reaction by the addition of water, and we've talked about this a lot. As plates are subducted, the pressure at about 100 meters begins to dewater the plate. Water is driven from the oceanic crust, and it doesn't cause the melting of the oceanic crust, it causes the melting of the mantle rock on top of it. And then that mantle rock moves up through the asthenosphere and even into the more rigid lithosphere part of the mantle as a partially melted magma, and then it pools. It gets to this layer, this differentiation layer between the continental crust and the mantle, still part of the same lithospheric plate, and it pools there, and there, because it's very hot, we're talking 1,500 degrees, there it will then begin to melt this silica-rich rock that makes up the continental crust. And as I said, silica has a lower melting point, so it melts first, which means this magma becomes very silica-rich. So what started out as a low silica, low viscosity, basaltic magma gets up here and then takes on silica and becomes silica enriched. It becomes a high silica andesitic or possibly even a rhyolitic magma. So most of all volcanoes are found around the Ring of Fire. We've talked a lot about the Ring of Fire. This is where our volcanoes, this is where our earthquakes are, and this is where our deep ocean trenches are, and this is where our composite stratovolcanoes are, and we have volcanic activity, heat flux certainly along the spreading ridges. We have a hot spot here that is creating the Hawaiian Islands, and then you have a few randomly distributed volcanoes in the interiors of plates, but mainly this is where we find most of our volcanoes. And here is sort of an example of the different types of volcanoes, and this is in your book, probably much easier to see in your book, but Hawaii is a hot spot where magma rises up to that mantle crust boundary and then it rises up to the crust, and because the oceanic crust is basaltic and low silica, you get a basaltic low silica magma creating shield volcanoes like we find in Hawaii. Now you get all along, and I mean all along, from Fuji all the way up into the mountains of the Aleutians in Alaska, right on down into the Pacific Northwest with the Cascades. These are all your composite volcanoes that occur from some type of plate convergence. Now, if it's our island chains, it's two oceanic chains, two oceanic plates converging, and one subducting under the other because it's older and colder and more dense, and then water is forced out, creating partial melting of the mantle rock, and it bubbles up through a basaltic crust, creating a basaltic magma in our volcanoes. And it either creates a volcanic island arc, or it's going to create a continental island chain or a continental island arc. And we see that with this convergent boundary where you have the oceanic plate subducting under the continental plate, and you get your continental arc. And then you also have your East African rift zone where you've got some basalt that comes up. There's also some andesitic magma there as well. And then a couple of other smaller types of volcanoes that you might find in different parts of the world. One of those different types of volcanoes is intraplate. This is your mantle plume, and this is your hot spot that rises up through the mantle, gets into the crust, melts the crust, and that crust bubbles up. That melted low silica magma, it's melting oceanic crust here, bubbles up to the crust and creates a flood basalt. And then eventually you start to get these volcanic hotspots that form. When that original kind of magma chamber floods out onto the ocean floor, it creates a flood basalt, but the tail just creates this hotspot, and that hotspot creates that individual volcanic activity that turns into your island chains. So that was Chapter 7 from Foundations of Earth Science, the 8th edition, written by Lutgens and Tarbuck and brought to you by Pearson Education. We learned about volcanoes and other types of igneous activity. Now, second only to plate tectonics, I think, to me, one of the most interesting things about this course, one of the interesting subjects, is this concept of geologic time and the tremendous span that makes up the history of the Earth. And we're going to tackle that in Chapter 8 of An Introduction to Earth Science.